All right, so let's get started. Today is February 23rd? Okay. February 23rd, CSTN 283 and 235 Building Energy Efficiency. This is John Freer, and I think first we're going to get started back a little bit. I know last week and the week before you guys jumped into a lot of the building science principles and the basics, and we'll revisit those. But even before that, one of the things that's pretty important is really the composition of a building and some of the different systems and strategies and assemblies that we're going to talk about, and starting back from the very basic sections of it. And so this textbook definition of what a building is, and this is, believe it or not, if you try to pronounce that name, you'll all get it wrong unless you know them. It's pronounced Seabrick. There's way too many consonants in it. But the second part of the definition is really what we're looking at. A building can be a lot of different things, but it's the environmental separator, and that's really what it's designed to do. It's designed to separate the indoors from the outdoors. And thinking about the building in that context is really one of the most important things, in how we control all those different things, from the temperature to the moisture migration, air movement, and we do it in a safe and healthy manner. And we're not going to get into the first history of buildings. We're going to talk really in the context of our architecture and our building history in the United States, and really where we've come started from very simplistic design. It was indigenous materials, whatever was a local material was used. And one of the reasons that most buildings in the early 20th century didn't have insulation is we just really didn't have access to it. And so as buildings developed, we started to understand how to control them, how to keep the heat in them. One of the things that's really happened is they've become incredibly complicated. And not all the buildings are the same. So we'll go through a little bit of the different building types and understand applicabilities and codes. But one of the things we have to do is understand the components of the building, the systems that go together, and how to start to monitor those in regards to energy usage. So really quickly, and this is one of the things that the codes differentiate between. It's also the difference in the energy performance, how we design buildings. It's very dependent on the size of the building and the use of the building. And the concepts that we use and the materials that we use for single-family and multifamily homes aren't necessarily the same ones we use for commercial design and urban design. The way the codes are broken out are similar to this. You've got residential, single-family, multifamily, and that's basically anything up to 4 stories high. Anything after that becomes a commercial use application. Mid-rise and high-rise are both mandated under the commercial codes. And then different types of buildings have different types of use. And this is when we start talking about energy use intensities, we'll talk more and more about the different types of use, because just as the buildings aren't used for the same thing, the energy intensities and the strategies that we use to control those aren't necessarily always going to be the same. So given that we have all of those different types of buildings and a lot of different wall assemblies, and we'll go through some of the different kinds for basements and above grade, there are still a lot of similarities, and there are a lot of things that we have to look at when we're doing our energy use intensities, and we're looking at our energy modeling, and we're looking at choosing which building systems we use. And one of the biggest ones is climate zones, and we did talk about the different Department of Energy climate zones. And this is where what you guys have worked on the past couple weeks is one thing to really understand and why it's so important. So what Brad had covered was talking about how heat moves in and out of a building. You guys talked about conduction, convection, and radiation and how that heat transfers from one side of the building envelope to the other side. And it's important to understand that the differentiation between climate zones can have a huge impact on that. You also talked about moisture migration, and we'll get fairly deep into the weeds on that when we talk about wall assemblies and structures. But again, going back to that whole concept of what the building does is separate the inside from the outside. The biggest part of it is controlling that heat transfer and understanding which way the moisture is going to move in that. So the assembly details are similar, but it depends on the location. So just real quick, and I want to revisit it so I know that you guys got it, and you did go through heat transfer, and we're going to get into conductive and convective calculations in that. Did you talk about any did you talk about condensation inside the wall cavities and moisture migration in and through the wall systems? Okay. We'll go through that a little bit more in depth when we get there. But like I say, the basic parts of the building science, I think, we'll go through those a little bit more in depth, but I think it's just important to know the separation between the inside and the outside. Again, depending on the heat load, the types and the quantities of the heat generating equipment, whether it's even heat generating equipment or cooling equipment, we tend to not think as much about cooling load, but when it comes to building energy use intensities, cooling load far exceeds heating load in the United States and what we consume in our energy. In a lot of the cooling climates, we're using probably twice as much energy as we are in some of our heating climates. And again, I want to back up on this because a couple people I had talked to in the last couple weeks, and these are things that we're really going to have to look at when we start looking at assembly details. And some of these might seem fairly elementary, but I want to run through them before we start talking about the thermal envelope. And when we talk about foundation constructions, we've got three basic kinds: basement, slab on grade, and crawl space. And these are all pretty straightforward stuff, but once we start thinking about them as a system and incorporating them all together is when we really have to understand a little bit more in depth as to how they all work. So real quickly, I want to visit these, and if you've got more questions on these, I know, so for my students in here, we've actually worked on a lot of these and we've installed some of these, but have you guys do you have any experience or done any basic review of construction methods and materials? And some yes, some no. Okay, well, this might be a review for you. Hopefully it's a good review, but let's just go through them real quick. So in the basic building process, the foundation is the first part. It's what everything rests on. Slab on grade is probably one of the minimalistic foundations that you can put in, and the term basically just comes from a concrete slab that sits at or near grade level. There's not a hole dug. They maybe come in and move topsoil off, but it's basically at grade or ground level. Just an example of one with some foam details, and this is where when we get into the thermal envelope here a little bit today, hopefully all of this starts to make sense and you know why it's important to know the difference. Just a couple other examples of it. And one of the things that I want to point out too when we talk about the thermal envelope, in this detail you can see they've got both on the exterior of the slab and underneath the slab. They've got in this detail a foam insulation layer, which is now part of the code, but it's one of the bigger areas in a slab on grade foundation where you get significant heat loss. We'll talk about and did you guys talk that much about conductivity of the different materials and K values and yeah? So you understand that it's a great material when it comes to thermal mass and holding heat, but it's not as great when it comes to stopping heat. So it's got a lower R value than a lot of the different materials. So anytime you've got it in ground contact, you always want to have it insulated. Crawl space, basement types, and this does require a little bit of excavation, and the main reason that you'll see crawl space in buildings is for either if you've got a high water table and you can't be directly right on grade, or if you're putting utilities or mechanical, plumbing, electrical, mechanical, running it down underneath, and you can see some heating pipes down in there. And we're going to go more and more about this, and you guys will start to look at more details. And once we actually get into houses, that's the other part where it's really good to understand these different foundation types. Not because you have to build them, but you need to find the problem areas. You need to know where the problems are. And so crawl spaces and basements, one of the biggest differences between those and a slab on grade is that you start to have an integration with the rest of the building. And anytime you've got a connection, you've got a chance for air leakage, improper insulation, improper air sealing. So that's where it becomes important to start recognizing these. Same thing with basements. Basements can be finished, they can be unfinished. And again, they're just, has anybody not ever been in a basement? Fairly straightforward. You can think of a basement as just a deeper crawl space. It's space underneath the above grade part of the house. And again, it becomes an area of fairly significant concern because you've got ground contact with the structure. The basement itself is in contact with the ground, so it's always conducting directly into the ground. Certainly recognize that basements are usually cooler, which is great in the summertime, not so good in the wintertime. It's because of that direct conductivity with the ground. And understanding once you get about 5 to 6 feet below the surface, you have a fairly constant ground temperature. Depending on where you are, what part of the country. Here it's about 54, 55 degrees. And so when you think about if a basement's going to go down 7 feet, 8 feet in the ground, you've got the entire basement slab and a lot of the basement walls, and they're in contact with 54 degree temperature. And so you've got to, if you're trying to keep your house at 70 degrees, you've got 54 degrees outside, you've got a 16 degree delta T constantly all winter long. And which way does the heat want to go? Hotter to colder. So it's constantly conducting from inside to outside. So basements are another big problem area. Just a couple different methods, and we'll talk a little bit, I want to talk a little bit more about different construction methods because they're pretty relevant to what we're talking about. Here's your traditional poured concrete basement foundation. I'll go over a couple options in a minute because we'll talk about them in both contexts. So the next point we have is our above grade walls, and as I said, not all building structures are the same. Different parts of the country build utilizing different methods. Main methods of above grade walls are CMUs, concrete masonry units. You're going to see this mostly in mixed climates, cooling climates, not very much thermal resistance in a CMU building, so unless there's supplementary insulation, and that's what this picture is showing a little bit. If you look at it here on this left-hand side, you can see supplemental insulation that's going over top of the CMU wall. Concrete tilt-up has always been a really popular, fast, efficient way of getting a structure up. Again, it's the conductivity of the concrete requires that it has to have supplemental insulation. And has anybody ever seen any concrete tilt-up? Did anybody go to Currents? Down McCormick Park? Go by there and check it out the next time you're there, and you can see it's a whole concrete tilt-up. It's just concrete panels tilted up. It's a pretty neat structure. Another popular assembly frame structure, heavy steel and light steel, and they're significantly different in their uses and how they go up. Heavy steel you'll see much more in a commercial application, larger, tall buildings. The heavy steel itself is the frame and the support of the building, and then they're wrapped in various types of skins. We're going to get to go over, in a few weeks, we'll go over to the new Missoula College building, which is a heavy steel framed building like this, and we're going to get to look at how they're wrapping the skin in that and the thermal envelope in it. And again, understanding the first part that I was talking about, and understanding that the whole purpose of the building is to separate the inside from the outside and to be able to control that. The biggest thing that helps in the control of that is the building envelope. So it's one of the most important things when we talk about effective and efficient building design. Light gauge steel, again, not as popular here in our part of the country, but when you start to get into different climates, especially when you talk about climates with heavy termite populations. Wood framing is very, very popular here, but when you get down to Louisiana and areas where wood is on the dinner menu for termites, you'll see a lot of light gauge steel. When you talked about conductivity, did you talk about, you looked at the metals and the steels, and some of them have K values of 1,000 to 1,100, where you're looking at 0.3 for wood. So with any kind of steel, there has to be a thermal barrier on it. You've got to wrap it and put supplementary coverings on it.
What's the cost difference between steel like that and 2x4?
Like so many answers, so the question is, what's the cost difference between wood framing and steel framing? The answer is it depends, which is the age-old answer in the construction industry. A lot of it depends on the labor costs. The materials costs on the steel is going to be a little bit more consistent, usually slightly higher than the wood costs, but your waste factor is going to be lower. You're not going to have crooked steel studs. They're all straight and they're all uniform. It depends on the part of the country that you're in. You don't see many residential framers here that use it, so if you tried to hire somebody to do that, it would probably be fairly expensive. However, in another part of the country where it's a lot more common, some parts of the southeast, and it would be more cost effective. It's a different wall assembly and a different method of building, and it's got other costs involved in it that might not necessarily be the same as wood construction. While it's always a good idea to create a thermal break and separate the wood from the outside, by code you don't have to. You will have to with the steel, especially in a colder climate. I've seen some residential steel frame buildings. It became fairly popular in the early 2000s, and a lot of it was because of the green build movement and promoting steel because it's infinitely recyclable. And at that point in time, wood was bad. Nobody wanted to cut any wood down and build houses out of it. And because it's such a highly conductive material, there were a lot of issues with it. I saw some houses that every they didn't get a good enough thermal break on it, so you could see every stud line. That would, the conditions were just right. If the moisture, relative humidity was there, and the temperature was right, you'd get condensation lines right down every stud. A couple other ones I saw had a thermal break, but they had their fasteners for the siding go straight through, and then you would see all of the little screw heads. So it's got some issues, but moving on, and this is a wall system, insulated concrete forms that are used primarily for basement systems, but they're also used for above grade walls. And one of the, as I said, with the concrete, one of the challenges with it is that it's in direct contact with the ground, so it's always conducting, it's always losing heat. With the concrete forms like these, they've got insulation both inside and out, so it creates that thermal break between the concrete and the ground. Also very low air infiltration, and so they're becoming more and more popular. Just a few other pictures of them. Again, you can use them for both above and below grade. Just a picture of using it for a walkout basement type. And most of them are fairly similar. They're just assembled like big Legos. One stacks on the other, and the concrete gets poured in between them. The reinforcement, steel reinforcement goes in there. And so when they're done, they're done. For residential, wood framing is still the most popular by far. It's relatively inexpensive, it's relatively easy, and one of the biggest things is that it's familiar to everybody in the trades. Wood framing and the practices and how the building goes together utilizing wood framing is pretty common among most builders. All of the trade contractors, the mechanical, electrical, plumbing contractors are familiar with wood framing. They understand what they can and can't do in wood framing. Most of the time they recognize when they can cut it and when they can't cut it. A couple quick notes. The two main types of framing that you're going to see are balloon framing and platform framing, and these become important to look for and to recognize, especially when we're going into existing homes and we're looking for some of those problem areas. The platform framing example, you can see you've got, and you'll see this primarily in multi-level homes, but you've got one wall system, and that stops at a level where it then has a floor system sit on top of it, and that floor system is the platform, and then the next story or the next level is going to sit on top of that platform. And we'll talk more about this when we start looking at wall assemblies, but this becomes important because it's one of the biggest problem areas in multi-unit structures. That connection between the lower floor or the lower wall, the floor joists, and the upper wall is one of the hardest to get sealed up properly. And we'll do some thermal imagery work and hopefully be able to see, and one of the things we'll do is hopefully be able to have everybody have their own time with thermal imagery and go out and do your own testing with it. But in a lot of older existing homes, when you're looking at thermal imagery, you see this red band between the floors, and it's this part that's usually not well air sealed, not well insulated. The other type of wood framing is balloon framing. You do see this a lot more in hybrid systems, but you have a continuous length of stud from plate to ceiling. This is important because it becomes a little bit more effective to seal it. You usually have a ledger or hangers or some other system to incorporate the floor joists so that you don't have that break. You don't have three pieces that come together that all have to be connected and sealed. And then we're going to talk a little bit more, and when we start looking at energy modeling and building assemblies, we're going to talk about advanced framing. And advanced framing isn't anything technologically advanced. It's just a structural and engineered method of using, that should say more insulation, less wood and more insulation. But through the course of just habit and practice, we've come to, as the industry repeats itself, we've come to just have a unwritten rule of how certain things go together. And a lot of times when it comes to especially residential wood framing, that habit and understanding of how things go together is completely excessive, and we use far too much wood than we need to in our structures. I'll go through a quick list of these, but the whole concept is to try to keep all of your framing members aligned. And we'll talk a little bit more about roof trusses in a minute, but they're bearing the weight of the roof, and so they really have to have support underneath them. So if you don't actually do your framing and lay it out properly, you end up having to add studs underneath trusses and floor joists. Another picture of how you see the wall studs down here line up directly underneath the floor joists, which line up directly underneath the wall studs above, which line up underneath the trusses. So you've got a complete stack of support all the way down with just one line of studs. If you have your floor joists and your studs not line up and you've got to add bearing in there, you're just adding more wood into the wall. And the more wood you add into the wall, the less insulation you have in there. So when we start to figure some, and next week we're going to work on doing some conductive heat loss calculations. We start to figure those conductive heat loss calculations, and you look at standard framing and the inefficiencies of standard framing versus advanced framing technique, usually you can see about a 10 to 15% increase by using advanced framing techniques and reducing the amount of solid sawn lumber that's in the wall. There's just a couple more details, and you don't have to memorize all these. Just understand the concept. The advanced framing is less wood. So here's a perfect example, and you see the 4-stud corner, which for probably the better part of 50 years is how most walls were built. And as you go into older homes, and again, if we start doing blower doors and thermal imagery, you can find this condition quite a bit, and you'll see how much heat loss is actually occurring in that. So with advanced framing, it moves on to 2-stud corners, California corners, and what it does, it allows, you've got less wood in the corner, so you've got less conductivity, and it allows you to get insulation in there. None of these are real rocket science concepts, but it's good to understand. Again, here's another one. This, on the left-hand side, where you see you've got a partition wall where an interior wall is actually connecting to an exterior wall, and that common 3-stud partition, that's how I learned how to frame. That's how I framed for 20 years until I learned about advanced framing. But as you can see, there's a huge gap in there, and oftentimes they would get framed and sheathed up, and you can find in a lot of older houses where there's just no insulation in there. So you can see the wider stud on the right-hand side. Single top plate connectors, and this depends on your seismic zone and what you're required to do structurally, but common construction practice has always been 1 plate along the bottom of the wall, 2 on the top, but in so many areas you don't need 2. There's no structure, there's no requirement for it. So if you think about the perimeter of an entire house, if you can reduce that whole wood plate around the house and replace it with insulation, it's yet one more increase in the efficiencies.
That's what they call the top plate, right?
Top plate, yeah.
You can toenail in your joists, or your ceiling joists, once you're setting your frame, or your
Right, and that's, so if you look at this, going back to keeping everything on layout, if your ceiling joist hits right over top of your single wall stud, right over top of your second wall stud, you're just reducing the amount of lumber. And you know, when advanced framing first kicked off, it was a little bit more of the saved lumber concept, but as it turns out, it actually saves money by putting more insulation in the wall, and it's far more effective as an energy efficiency measure as it is a lumber saving measure.
They used to do like the 12 by 12, we went to the 16 by 16 with proper lumber adjustments with the 2 by 4s, 2 by 6, you know, with 16-inch on center, and the study says it saves 40% on energy.
Well, you'll even find now 2 by 6 on 24-inch centers, depending on how, we won't get into shear nailing and attachments and shear wall structures, but you can reduce the amount of wood in the wall pretty significantly and still use.
And raise the thermal, or raise the efficiency of the house.
Yeah. So a couple more, you know, another wood framing is basic timber frame. Old school barn raising, but you're seeing it more and more with the advent of different types of skins that can be used. And this is usually just an internal skeleton, and then it's wrapped completely. The one that we're seeing more and more of now in wall assembly systems, especially for residential or structurally insulated panels, and these are this is a wall system that replaces the 2 by 4 or 2 by 6 framing. So there, you don't, with a timber frame, like I showed you in the last slide, a lot of times they'll wrap them with this, but these are actually structural. They'll take the place of the wall. And again, the whole concept of it is less wood, more insulation. The way that these are made, you've got an expanded polystyrene foam core, and on both sides of it are laminated skins
OSB.
of OSB, primarily OSB.
Yeah.
So there is no thermal bridging from inside to out. They're put together with a spline system rather than 2 by 4s, and if they're sealed up properly, usually about 50% better when it comes to air infiltration. Just a couple pictures of some of them going up. Most of them now are all factory pre-cut, so all the windows and doors and the bevels and the roof pitches are cut before they ever hit the job site, so they do go up pretty quickly. Again, it's got the foam core, so the R value, usually with the EPS, is about an R4 per inch. So if you've got a 4.7, I think, or 4.8 is what 2-pound density foam usually comes in at. So if you've got a 5.5-inch foam, which matches up with your standard 2 by 6 framing, you're anywhere from R24 to R26 in the walls. And with that, you're also at a much lower air infiltration. So the only knock on them is because they're made with EPS foam, it's a petroleum-based product, so they do have a fairly high global warming potential. But again, they're fairly efficient, and they do make for a pretty good building envelope. Just a couple other assembly methods that you'll see primarily in residential, and this is a double stud wall, and this is kind of on a really small scale what ends up happening in most all large commercial buildings. They've got an inner wall and then an outer wall, so that inner wall is either going to be that heavy gauge steel or concrete, and then they're going to have a skin on the outside, which is going to be their thermal envelope. And the whole concept, again, is to make that uncoupling of the inside to the outside, back to the basics of what a building does. It separates the inside to the outside, so the more separation we get on it, the more efficient it becomes. Some of the double stud walls, you'll see they even stagger all the studs, so there's even less chance of any thermal conductivity. then you'll see called a Larson truss wall or a structural truss wall, and these are just different variations in these can be pre-manufactured, even using the truss joists as the TJIs for the wall studs, so that you get much more depth in the wall. And the whole concept of these is just to be able to add more insulation. When we start talking about passive house, we'll look at some more of these assemblies. And I briefly touched on passive house a couple weeks ago, but one of the biggest theories in the passive house is creating a very, very high R-value wall. The easiest way to do that is to really thicken up the wall. You can pack more insulation in it. So we're seeing more and more of these structural truss walls and double walls, wide walls. There's a couple of slides in here when we talk about the thermal envelope and building assemblies. We'll talk a little bit more about different types of roofs, and you've probably all seen these different types of roof somewhere or another. And what becomes interesting in design is they all have their pluses and minuses when it comes to moisture protection, thermal protection. Some are far easier to seal than others. Some are far more effective. I'll talk about venting in just a minute. And they can have a pretty big impact on your thermal performance and on your overall energy performance. So understanding the different types of roof assemblies and what they are, and again, we're not going to go too far into them, but you guys can look through these and you should be able to identify the difference between a shed roof and a gable roof and a flat roof. In residential, most of what we're seeing now is all assembled trusses for a lot of different reasons, most of which is cost effective and ease of assembly. We'll look at a lot of different things. When we talk about trusses, one of the things that becomes an issue, I don't have the slides in here, but we'll talk about it in a little bit more in the thermal envelope. Trusses have evolved significantly in the residential world just in the last 10 years because we started adding increased insulation. And the very end of a truss, if you look at some of these like the scissors truss, the very end of the truss comes to a point, and that point usually ends up at the end of the wall. And so if we're trying to get a lot of insulation in our ceiling, but we come to a point at the end of the wall, we've all of a sudden decreased the ability to get that insulation in there. So we'll talk about raised heel trusses and strategies on that in our envelope, and I can show you, I think, in the next slide. The other main type in residential you'll see is just a rafter and ridge type of assembly. It's accomplishing the same thing as the truss, but it usually requires heavier lumber to get the spans out of it. And it does have, sometimes it's got its advantage when we look at how we're going to set up the thermal envelope and where we're going to set up the thermal envelope. So the other thing that we kind of need to talk about, and I don't know how much if you talked about this in moisture migration and movement and the importance of that, but vented roof assemblies and non-vented roof assemblies. And it becomes very important in looking at the thermal envelope and how we're controlling moisture. The concept behind these, in a vented roof assembly, your thermal envelope you're creating at the ceiling level, and the attic space is open and it's unconditioned. And so what you're trying to do is control that space so that it doesn't overheat, for one, because if you, for example, in a cooling climate, if you've got your thermal envelope at the ceiling level and you've got an unvented attic, it's going to heat up significantly. You could be 165, 170 degrees in the attic. So all of a sudden you've got a house that you're trying to keep at 70 degrees and you've got a 165 degree attic. You've got such a delta T, there's a significant heat flow, which in turn goes to significant moisture drive. It's also, and we'll talk about it in air sealing a little bit more too, and you'll see it in older buildings. It becomes an issue because when you've got, in a heated climate, when you've got that heated air trying to escape, and it escapes up through the thermal envelope, and it hits the cold roof, what happens?
Absorbed into the filter.
It condensates. It goes from moisture vapor to bulk moisture. Did you guys talk about that? The vapor drive and a little bit?
Yeah.
We can talk about that. We'll talk about that a little bit more, I guess, when we get into the wall assemblies then. Okay. So the other basic type of assembly is an unvented roof assembly. And again, why that becomes important is you have to understand those basic mechanics of heat flow and moisture migration, and you have to make sure that you're creating a solid thermal envelope that not only is going to separate the inside, the outside, and cut down that heat flow, but is also going to not allow any moisture to get inside of that cavity. Just take a quick break. Any questions and comments? I mean, that's a real broad 30,000-foot view of some of the ways that we build a building. Any questions, any comments?
What's that green sheeting they're using on the new Missoula College building as far as what they're wrapping it in? That's like an engineered.
That's actually part of the thermal envelope. It's a water resistant barrier with insulation in it.
Using an OSB that.
Yeah, you're not going to see on most commercial structures. You're not going to see any type of an OSB or wood cladding on it. They're going to use a steel frame and a wrap like that. Just like a Den's glass, it's a water resistant barrier, and it's the start of the thermal envelope.
What are they going to wrap it in after that? Are they just using like a metal siding or?
That's a good question. I don't know. I think they're doing some stucco on it, but I don't know the answer to that. Maybe they'll have siding on it by the time we get there, but yeah. The other part of it too is because you've got a heavy steel structure that is the structure of that building, and then you've got light gauge steel that's framing up that curtain wall. That makes the thermal break. That cuts the steel off from being exposed to the outside to cut down on the conductivity. All right, let me stop this. Maybe. You guys can take a quick break.
Most of those corner pieces, what you're talking about, for the corners of the actual walls are also applied, so you can put your sheetrock up and have something to screw in, so you've got that.
Right, so there's a nailer on them,
Right.
correct, yep, yeah.
Because that's all we usually just build, the square boxes and then situate them that way, but we'd always put the batting up before we even framed it.
Right.
So it'd always be insulated, because like you said, most people wouldn't do that.
I can't fathom
And
what.
floor trusses on the OSB, as I always thought, that's the thing to do is the panels with the insulation, because it's so, we use that stuff for setting up our pump jacks. You could walk the span of the house when you're doing siding, on OSB as a plank,
Right,
because it's so stout. We even calculated it where, I mean, it almost replaced 2 speed, you know, stand on there would replace solid beams, you know, on weight carrying over different spaces, because we had to correct different blueprints on engineering, because they didn't give us enough